have even more participants than yesterday. Okay, so the first talk is by Ines Aniceto from
Just a second, I'm not sharing my screen, am I?
No?
Oh, right, sorry. Just 1 second. Can you see it?
Yes.
I'm so sorry, I forgot about it.
Don't worry, we all have the, let's take back the technical issues we used to have when we did these things in person. Okay, so she's going to talk about ADS-CFT inspires massive massless interactions in integrable field theories. So,
thank you for coming, and hopefully, yeah, this is work that I've done a little while ago, and for the people who have heard the talk, I'm sorry, I don't have a huge amount more to say because during the last year it's been basically non-existent for most of it. So I will be talking about some ideas. So I'm not talking about ADS-CFT, but I'm taking the information from what we've seen in ADS-CFT to work on a different class of models of field theories, which is the homogeneous Sine-Gordon models. So what do I mean that it's ADS-CFT inspired? Well, we know that in ADS-5-CFT4 we have integrability, and that allows us to calculate, for example, the anomalous dimension of gauge operators, or well, semi-classical or all orders, depending on what we're hoping for spinning strings as well. And in particular, if we look at the usual beta ansatz equations, what we get is the leading energy, and then if we can upgrade it to using the integrability, like either TBA or meaning Lucia is not doesn't need integrability, but of course, when we have an integrable model, we know the exact S matrix, so Lucia corrections actually can be calculated much more easily. And basically what we get is the corrections to the energies, to the leading energy. One thing about ADS-5-CFT4, of course, is that all excitations, when we're calculating these corrections, are massive. So meaning everything is very obvious, what is exponentially suppressed, what is not, what is leading, what is not. While when we're going to ADS-3, both backgrounds, sorry, I did not write the backgrounds here, but what we have is both massive and massless excitations. We know the S matrix. We know that one thing that is interesting is that even it's an integral model, it has a sector, an interacting sector between massive and massless excitations, and all loop beta ansatz equations are known. But what is the consequence of having both massive and massless excitations? Do we know that there are consequences, direct consequences on things that we cannot do that we could do in the original case of ADS-5-CFT4? Well, one thing that we can do is look at SU2 circular strings in one of the backgrounds and perturb it. And basically what we have is the classical energy given by the original classical solution. And then we have a semi-classical correction. So we can do this from the worldsheet point of view. And what we get is a sum over frequencies. So the energy correction is just a sum over frequencies, and this can be done. And also we can use the beta ansatz, expand the S matrix at strong coupling, and calculate the correction that we get from the beta ansatz directly. And what one finds, of course, is that these two do not match. So the beta ansatz, there's something missing in the beta ansatz, and of course, the whole point is that it's related to the fact that we have this massive massless interaction. So I will talk a little bit, a moment, just about Lucia corrections and what we found as from the point of view of Lucia corrections that explains this mismatch. So if we're looking at the energy spectrum for a system that is of finite size, L, we have that beta equations are exact, and they're basically given us by giving, in general, I'm talking about diagonal beta ansatz. Of course, there's generalizations of this, but I'm just talking about the simplest case. And basically, I have here my two particle S matrix, and I have the beta equations, and the energy is basically given by just a sum of the dispersion relation, so the energy of each particle with the momentum J. In particular, of course, this dispersion relation is known for different models. In the relativistic case, is the usual simple relativistic dispersion relation. For ADS5 process 5, it's, for example, more complicated, the relation with P. We can change between P, and this is going to be helpful to change between P and the rapidity by doing this change that comes from the relativistic field theories. So as I've mentioned, what's the validity of the beta ansatz? Well, it will describe for us the full system for discrete L, but meaning for field theories, of course, this is only an approximate solution at very large L. And then if you want to calculate corrections in large L, what you need to find is actually, you'll have virtual particles in the field theory circling the volume that you've taken large, but they'll be virtual particles, and those will give you the corrections, the semi-classical corrections to the energy. This is just a brief recap of the one formula that I'll take from Luscher, which is, okay, like so I will take a single massive particle state and a very large volume L, and what the Luscher corrections give you is the mass shift, the mass shift of the original particle. And the interesting thing about the Luscher corrections is that, the same way as it will be with the TBA, is that the only information that goes into these corrections is the infinite volume data. So the infinite volume S matrix. If we know the S matrix, we can calculate these corrections as well. This is one particular type of Luscher corrections is called the F term, which corresponds to having, like, this is my physical particle here traveling, and then this is my virtual particle circling the volume L. There's other types of terms in Luscher corrections, and there's also extensions of these corrections that include multiple particle states and also multiple virtual particles. So one thing that I want to say, that I want to definitely mention, is that in massive theories, this correction is going to be exponentially suppressed because this exponential is very small. Meaning it's given this energy. This is the dispersion relation. This is m cos theta, and basically that means that the minimum value of this is ml. So it's e to the minus ml. L is very large. M is finite. This is exponentially suppressed. So that's what happens for finite theories. And of course, if you want to find the general case, you need to actually, for at least when you have integrability, you need to determine the full thermodynamic beta ansatz. So this is what I had mentioned. So in ADS3, we have a mismatch between the calculation in the worldsheet and just the contribution from the beta ansatz. We know that it's not enough. So what is the role then of the massless excitations? Let's look then at Luscher corrections and assume that we're taking the virtual particle to be massless. So this is again that term that I showed you in terms of the Luscher correction. So it's the correction to the energy. It has that exponential that I said for finite mass is exponentially small for large L. It has the infinite volume S matrix here. And I want to calculate this. And this is a sum over all particles that are basically all virtual particles inside circling the volume. So what do I take how do I take the massless limit? I can't just take m naught to be 0. I need to be careful because what I want is actually, meaning I know that even in a relativistic particle, the momentum will be finite. The mass will be 0, but the momentum will be finite. So I need to have the P momentum finite while I take my m naught to be 0. So this is what happens. So for mass non-zero, this is the dispersion relation with respect to the momentum P. So I'm writing E as a function of P. P has this shape, E has this shape, and I'm just writing one in terms of the other. So this is here is the E of theta, or E of P if I want. And basically for mass non-zero, it will always be non-zero, which means that this will always be suppressed, this exponential. But if I take the massless limit, meaning it's non-zero still, except at the origin. At the origin is not zero, so there will be a non-trivial contribution, basically, if we zoom in the region around zero. So somehow, in the massive theories, we had these corrections that were exponentially suppressed, and now we have contributions coming from this little bit that are not exponentially suppressed. So what happens here when p equals to 0 is that all wrappings contribute at the same order, all of them. So we don't have an expansion in exponentials for the TBA. We don't have anything, as we'll see. We'll just have that the full TBA would be needed in order to calculate these non-trivial interactions. So meaning it is known from massless TBAs, of course, that this is that one cannot have an expansion in the exponentials. But here we're more interested in understanding what happens if the physical particle is massive and the virtual particle is massless.
So I have a question, maybe. This is a relativistic, right? But if the theory were non-relativistic, I guess what you would have there is rather the mirror momentum rather than the
momentum.
Than the energy of the original. I mean, like
here, you mean?
Yeah, that would be the mirror momentum, right? I mean, I guess qualitatively nothing changes, right? But
yeah, this is just indeed, yeah. Mm-hmm. You'd have to be a bit more careful. Meaning, I'm just really going through the very basics, but yes, indeed.
Okay, thanks.
Just because there'll be lots of slides with a bit like this. The formulas don't matter, but this is the things that will always show in the different that I will always show in the different models. Is that so? I need a TBA, so I want to calculate the TBA and the energy of some particular integrable field theory, that like a particular number of physical excitations, and basically I'm taking finite volume L, but L very large. And what happens is that the only thing I need again is the infinite volume S matrix showing up here. So it shows up here for the pseudo energies, and it shows up here for the kernel, the interaction kernel, which is this K. Again, if we have that the theory is massive, these will all contribute as exponentially suppressed terms. So in order, here you can see that I have they have the physical rapidities, and I have the rapidity that then can be of the virtual particle. And basically to determine the physical rapidities, I have a quantization condition, which gives me that those rapidities. And then again, the energy is the sum over all these are the original your original energies with the physical rapidities. And then we have a correction here, which again, as I mentioned, this log will be exponentially small if we have a massive theory. So the question then is that I know how to write a TBA with massive particles. There are TBAs with massless particles, but typically what happens is that if you have both massless and massive particles in a theory, the two sectors decouple. You can study them separately, but the interactions don't. The interactions, there's no interactions, and the interactions don't contribute to the massless sector, doesn't contribute to the massive sector, and vice versa. So how do I study a TBA with non-trivial massive massless interactions where they contribute directly to the physical energies? And what we'll do is we look at a class of field theories which have mass parameters, and not only, because the mass parameters are not enough. And what we'll look at is the homogeneous sine-Gordon models. So the homogeneous sine-Gordon models are an integrable family of field theories which generalize the complex sine-Gordon theory. And we'll focus on the SU3K homogeneous sine-Gordon models, which have 3 adjustable parameters. What are the adjustable parameters? 2 masses, and then a rapidity shift or offset. And this rapidity shift will play a major role in the fact that we'll be able to actually recover interacting massless massive sectors. So today we'll look at 2 theories. It's the SU32 and the SU33. The SU332 is simpler, so that's why I will start with it. It has two types of particles, one with a mass m1 and one with a mass m2. It has a non-trivial massive, we'll see that it has a non-trivial massive massless interaction, but the thing is that it has a trivial massless interaction, which is something that we don't want. And that's why then we upgrade this to the SU33, where we have 4 types of particles, 2 of mass m1, 2 of mass m2, and then we'll have non-trivial interactions, both massive and massless. This is going to be our goal. So, okay, then the setup for the first example of the homogeneous Sideburn model. Again, I said I have 2 particles, one with mass m1, one with mass m2. I know the S matrix. It only depends on the difference of the rapidities. And basically it's given by this. It has, here it's just -1. Here we have a 10H. So what I will use throughout the rest of the talk is that theta means that I'm talking about a massive particle. Phi, I'm talking about what will become a massless particle, a virtual massless particle. And the hat means that it's the physical rapidity, the rapidity that obeys the quantization condition. And also, I will choose that my physical state will have only excitations of type M1. This is here, it's meaning it's M2 will become 0. So of course, I would only have M1. But in the second example, where I have 2 types of particles of mass M1, I will just choose always 1 type of particles. And what I want is to study the excited state TPA. So these, like I said, this is the same as the TBA before, where I write the pseudo energies, basically, which are given by the original term that is common from the beta ansatz. But then I have here extra integrals, which in massive theories are exponentially small. So these L's are just that log that I've written before. The K is the interaction kernel, meaning this is just, they're big expressions, but the main thing is that I have these pseudo energies that have these integrals, and these integrals will contribute to the energies from to here, but actually they don't only contribute to here, because when we solve the quantization condition, because we're solving for the epsilon1, which is this one, also this integral will change the quantization condition as compared to the original beta ansatz. So these integrals that show up here contribute both here and here to this integral. So what happens if I drop the integrals? If I drop the integrals, I just have the beta ansatz, the original one. And that gives me, and I can calculate also the physical rapidities in for just using the beta ansatz itself. And basically here I get polynomial accuracy, meaning that I get solutions that are powers, there are sum over powers of L minus 1. I'll have 1 over L, 1 over L squared, 1 over L cubed, and there won't be any exponentials because I dropped all the integrals. In massive particles at large volume, as I've mentioned before, these LIs, which are these logs here, they're exponentially small. So they're exponentially small, and basically, if I'm not interested in looking at exponentially small terms, so I can just neglect them. So here I write the energy a bit like what I've said before. So I can say that the energy is the energy of the beta ansatz, plus this is the contribution from those integrals when they correct the rapidities, and here it's the contribution from the integral itself in the energy. So which there I calculate, I call this delta EQ from the quantization, delta E int from the integral. So for massive theories, both of these are exponentially small, and like we said, basically up to exponentially small terms, we have the energy of the beta ansatz. What we're interested in now is doing the massless limit. So M1 is my physical particle, M2 is my virtual part, it will be my virtual particle, and I want to take M2 to 0, and not just M2 to 0, M2L is also goes to 0. So L is very large, but M2L as a quantity is also 0. So what happens to the integrals in this case? So I'm looking now at the delta E int, just because it's simpler. And what I have here, this is the term that comes with the L1. L1 comes from the physical particle, from the massive particle, and this will be always exponentially suppressed because this has an exponential that is exponentially suppressed for large L. But here is what we want to know. We want to know if this term can survive when M2 goes to 0. So I've written again what I want to do. I want M2L going to 0 as well. Basically, this is exponentially small, but L2 in itself will be of order 1. So L2 is basically 0, meaning it's also doesn't contribute, but it contributes if we zoom in for the in the phi when the phi is very large. So if phi goes to infinity or is very close to infinity, here you can see that I have the vacuum solution. So we've written here the vacuum solution, and here in blue, what I have is that it's the epsilon 2, which is what comes with the L2. You can see that for minus infinity or phi, it's still the same, but plus infinity, they differ. So if I could zoom in, do some limit that I would zoom in this region, I could capture the difference and how the massless excitations actually contribute to the original energy. So what we do, well, we want this momentum to remain finite when phi goes to infinity and M2 goes to 0. And such that, yeah, the relevant integrals become something like this. So integral in dp e to the minus LP, which is order 1 over L. Again, the momentum, we know from relativistic theories, the momentum should remain finite, even if it's a massless particle. How do we do this? Because just using the masses, we can't get that. They will always decouple. But actually, we do have, so we expect the massless sector to decouple as every S matrix element becomes constant. If I just do the massless M2 goes to 0. But the S matrix depends on another parameter, sigma, and we can use this parameter sigma to counteract the behavior when M2 goes to 0. So I do a double scaled limit. And what I do is M2 goes to 0, M2L also goes to 0, and sigma goes to infinity, such that this sum remains finite. So sigma naught is a finite coefficient.
Sorry, could you give a physical explanation of what this parameter sigma is, sort of physically from some worldsheet perspective or something, or anything really?
The short answer is at the moment, no. I think you can understand it from the Lagrangian point of view, but I don't remember what it actually is, sorry.
So it's just some random parameter in the S matrix?
I really do think that it's more than that from the point of view of, meaning if you look at the homogeneous Gordon Lagrangians, I think that there's some physical interpretation of what this is, but I do not remember what it is.
Okay, no worries. Maybe we'll
but
catch up later.
That's a good question, because I don't know what the equivalent would be in the world sheet specifically. Yeah.
Exactly.
Maybe related to that, can I ask? So I didn't quite get, is it obvious that you cannot get a finite limit by doing double scaling in M and theta, the rapidity, which is what you would normally?
It's not obvious, but
it's not.
But it is. And we've tried, and no, you can't get. Yeah, basically you can get this. This will go to a finite value the same way as the Lucier corrections were going to finite value when P was close to any. You can get P finite and you can do an integration in P, but basically it's not enough to counteract this M2 going to 0.
Mm-hmm.
And it basically kills this contribution. You don't have it.
Okay, thanks.
So you can do it from the pseudo energies, but then from this point of view you don't get it, as far as I remember. But yeah, so something else needs to happen. You need to do the two of them, and even different different contributions between sigma and M2 don't quite do the same thing. I think there is a I don't think this is completely fixed, obviously, but I think that it's meaning that the sigma and log of M2 definitely have to be of the same order. One thing that I want to already mention is that I chose sigma to go to plus infinity, and actually you can choose sigma to go to minus infinity as well. And as we're going to see, this means that actually either from these models, I can either get the right moving particles to keep an interaction or the left moving particles to keep an interaction. With just one sigma parameter, you can't do both. So, and choosing sigma go to plus infinity means that I'll keep the right moving particles only, as we'll see. Okay. So this is the limit that I'm taking, the double scaled limit. P for large phi is this because it was sinh of phi. And basically for large phi, P is just given by this. And the S matrix just becomes something like this. So for P greater than 0, it's non-trivial. For P less than 0, it's a constant. So this is the S21, so massless massive interaction. S12 is similar, and the other elements are constant. So the pseudo energies become something like this. So you can see in terms of P, there's a non-trivial result here. This is going to be of order 1. So this is actually of leading order. The epsilon 2, again, I ignored anything that is exponentially suppressed. So epsilon 2 would have contributions from epsilon 1, but they would be exponentially small. So those we didn't include. So we can also define the physical rapidities in the same way. And the energy of the physical state, I'm writing now here. I'm interested in looking at this delta E int to see what happens. And the delta E int comes with this integration. By the way, because we have this separation between P greater than 0 and P less than 0, we have a constant contribution from P less than 0. It only contributes 1/L effect, and that is it, while the P greater than 0 has this non-trivial integral.
Sorry, maybe just a follow-up. Still trying to learn about this sigma. When you're scaling sigma on the previous transparency to infinity and M2 to 0, what does M2 times sigma go to? In other words,
sigma.
In other words, is there do they scale in some, is there any relation in the speed with which you?
The short answer is I don't know, because it's M2 e to the sigma, right? That has a, you can see that M2 e to the sigma is it's actually, sorry, yeah, it's M2 e to the sigma that has, that is finite. Of course, you could assume that there would be some kind of dependence between the two of them and see what, if you could expand in.
Okay, no, but I think you're answering my question. I'm sorry. Yeah, that last formula means that there is some relation between how you scale. Right.
As I said, meaning whether you could have here different constants, you can't have here different constants in front of the log. But you can obviously you can add, meaning the log divided by 2, the M2 divided by 2, it's just a change of the sigma naught, so that doesn't make a difference at all. So yeah, here now P is finite, sigma naught is finite. So all these contributions you can calculate. And again, this is the delta E int. So this is the solution. You can calculate this. Meaning it's, so delta E int, here's the contribution from P less than 0. Here is the full expansion I just wrote here what that exponential was, e to the minus e minus epsilon 2, and you have this. And you can expand this and calculate in orders of 1/L. The interesting thing, so this is the rapidity. The rapidity can be calculated from the quantization condition. I'm taking one particle physical state, so it's just one particle. And I have a C1, a C2. And this contribution here shows up at 1/L cubed as the correction in delta E int. So one very important thing is that, so you could think that I would be able to actually expand this integral in these exponentials, but I can't. So because all these wrappings will contribute all to the same order. So if you did expand this exponential, all of the exponential will contribute at the same order. So it's not useful to do that, but you can do something else. You can expand this in L-1, and what you keep finite is Y PL. So L, P small, L large, and you have an expansion in L-1, and you can calculate this, this integral in exact form. Another note is that, of course, that we also have corrections from the fact that we're doing this change, this massless limit. We have corrections to the quantization condition, but these corrections actually appear only at order L-2, and the delta EQ is also of order L to the cube. So the first two terms do not have any contribution from the quantization condition. So,
Ines, can I ask you just a quick question? The S matrix that you get in the limit seems to have some sort of non-analyticity. Well, it's written in P variable, but it's very interesting to see that it is.
sorry,
Seems to be sort of discontinuous.
I seem to have lost it. No, it's above, so it can't be. So this is the limit, TBA limit here.
Yeah, it's 1 for P less. And probably in the S Mandelstam, is it still analytic in some region, I suppose?
Is it because you're doing the limit differently depending on whether sigma goes to plus infinity or minus infinity? I mean, you have this split. Maybe is that?
Oh, is that so? These are two different limits, or?
No, meaning here for the calculation, I do sigma goes to plus infinity.
Right.
If you did sigma to minus infinity, you'd get a different behavior here.
Mm-hmm.
But then you get this funny bifurcation depending on P. So it's just not obvious to me that it's still, well, it retains some analyticity, but it probably does in the appropriate variables.
I thought it did. But again, we were playing around with how does the S matrix look, but honestly, it's been a while. I don't remember.
No.
But I think it did. I think it looked very odd, but it behaved quite nicely.
I see.
There was no peaks of anything.
But it's a little bit because you're zooming in this regime where things are linear, right? And you have to choose sort of the slope, and then there will be a natural split between sort of chiral and anti-chiral things, I imagine.
I see. Okay. Yeah.
So let me just, the summary is that, so we have a double scaling limit that we use both, well, we zoom in on that region of the rapidity but we also include the shift parameter. Massless particles contribute to the spectrum of the massive states. They contribute non-trivially, but as I mentioned this before when I talked about the S matrix, massless interactions are actually trivial. So this is as much as it goes. And we know that this should keep on going because we would have also massless contributions and the multi-particle states in the circling the volume that could interact with each other in principle. So this is not enough because there's no interactions between massless particles. So what we do is we enhance our model and we go to the SU33 homogeneous sine Gordon, where in this case we have two particles of each mass. So we have four types of particle total and two particles of each mass, M1 and M2. So here IJ labels mass, AB labels the particle. And also we still have one shift parameter. So just so that if you want to see this, the S matrix is given by, is diagonal and is given by this. In the massive and massless, massless, we have this. So for the same mass, and here for different masses, so the interaction between the two masses, we have this matrix here. So basically there's a sigma j, but sigma j is just one parameter. Sigma 1, 2 is minus sigma 2, 1. And this is what this symbol means. Ooh, and here I have a mistake. So TBA, now we want the excited state of massive particle, physical particles. So my state will be of one type only. So I'm taking type A equals 1, mass M1, and that's it. My physical state is going to be this, and this is actually going to simplify my equations quite a lot. So yet again, TBA. So we have the pseudo energies written by this. Here are our integrals that we want to analyze. This is the same idea. We have our logs, which for massive particles are exponentially small, for massless are not. The interacting kernel, physical rapidities, because it's just the 1-1 sector, because it's just one type of particles. And then the energy of the physical state, the original beta ansatz, well, plus with the corrections for the physical rapidities, and then our integration. So I now want to take the same massless limit. What are the simplifications? I'm taking M1 equals 1. It really does not matter in the end. I will drop all exponentially small terms that come from massive excitations. And I will only take, as I mentioned, physical particles are only of one type. And because I do this, especially the physical particles, happens, I had 4 pseudo energies, but it happens that they're complex conjugate of each other. So in fact, I only have 2. So this is the big simplification in the equations. So I only need to deal with the epsilon 1, 2 and the epsilon 1, 1, and I have everything. So these are the 2. They look ugly again, but I have here 2 parts. So you see here, there's the L and the L bar that shows up here. The L is the same as I've written here. So these are the 2 pseudo energies that are relevant for us. So as I mentioned, we have 2 relevant equations for these 2. The physical rapidities are still given by the same epsilon 1, 1. And now the energy is calculated by L12, and you can see that the other contribution comes from L12 bar. So of course, energy is real, so it had to be complex conjugate of each other. And now, how do I solve the TBA? This is a much more complicated TBA, of course. So one thing is I can solve it numerically by doing what? Taking large L, small M2, and keep M2L still small. It has to be small enough, otherwise it won't match, it wouldn't compare to our double scaled limit. And also I want to take the double scaling limit, which is what the same thing as I've done before. If I do this, again, I get the S matrix gets a simplification as well. So now I have, I haven't written here what S is, just this thing. It's that symbol that I've written before. I can show you if you want. And now it's defined with respect to the momentum P and the physical rapidity is theta K. And of course, for P less than 0, again, only right moving modes contribute. So the P less than 0, the S is still constant as well. So this is the pseudo energy that will matter for us, that we need to calculate. The other one only matters for the physical rapidities, and I just wrote what the equation for the physical rapidities would look like for one particle, one single particle, physical particle. So, and the energy of the physical state has, again, this delta E int that is given by this integral, which is 1 plus e to the minus epsilon p. So this is the epsilon p. Again, I want to calculate this. Epsilon p appears inside here as well. So this is an equation that we still need to solve. How do we solve it? This is the result. I will talk about the result, but first I want to mention how to solve it. For large L, again, I expand in L minus 1 and keeping y, p times L finite, fixed. So what I get is that I get an expansion for epsilon of p, which are functions of y, and with powers of 1 over L, and also for the rapidities, I'll have in powers of 1 over L. I plug this into the delta E int, and you can find that the solution, basically, this is the contribution coming from the quantization condition, and delta E int has a leading contribution that it has a log with the F0, and then it has all these linear contributions from F1, F2, F3, and then on. And this is the result that you find here in this plot. So you can see that, so in red, it's the just including the 1 over L 1 over L term, of the delta E int. Here it's up to L 1 over L squared. And here is up to 1 over L cubed, so includes 1 over L cubed term. And this is a comparison with the numerical solution. So the dots are the numerical solution. For M2, 10 to the minus 12. And yeah, and L varies, of course. The larger GL, the better the comparison between the two things. Just to tell that here there is an issue, but it's because we have a lack of precision in the numerical calculation. It's not that it's nothing weird happening. It's just a lack of precision, and something strange happens in the numerical calculation after this point. So you can see that indeed the calculation follows the numerical calculation for taking L large, M very small quite closely. So the first conclusion, the spectrum of massive excitations depends on the massless sector, includes self-interactions of massless-massless, because all of these extra terms are actually coming from the massless-massless interaction. Unfortunately, only either left or right moving massless particles can be coupled to the massive states. And also, this was very important in our analytic calculation, is that you can't expand in these exponentials because all of them contribute at the same order in L. But you can expand in L minus 1 as long as you take that combination P times L fixed Y, and then you expand in that Y. So just a brief thing. Sorry, that's 5 minutes extra. Some things that would be very interesting to understand. So one of them would be what type of models can we include another shift parameter that would allow us to include both right and left movers? Or is there a different theory that would allow us to do that? Also understand the same limit from the field theory point of view. What happens to the Lagrangian? What happens to the actual fields when we take this limit? Well, for that, of course, what is the shift parameter? What does it do in the Lagrangian theory? And also towards IDS-CFT, of course, it would be really good to incorporate massless modes in the full TBA. Can we learn anything from these formulas to help us understand or guess what would something like that would look like? Of course, that would be very wishful thinking, but still. So, thank you.
Yes, thanks, Ines. Any question?
First, I have another comment. This sigma that goes to infinity, and then you're basically left with the mass. Could it be that it's some sort of dynamically generated mass in the field theory? I think sometimes when you get the dispersion relation, which just becomes m e to the theta, it's telling you that there's some dynamical generation of mass. If one were to follow really the Lagrangian and then quantization.
You're saying like taking the sigma to infinity.
Yeah, this combined limit
where
m2 e to the sigma is sort of mimicking something that is quite non-trivial on the Lagrangian level. Some sort of mass parameter that is generated by quantum correction, perhaps.
Perhaps, but then it's that wouldn't correspond to any of the excitations, right? It would be something different. How would you?
Yeah, I don't know. It's.
I haven't done it, so I don't know the answer. But yes, indeed, something must happen. And again, I think it goes into Bogdan's question about like what is the role of sigma? What is sigma physically? Which which must be the part of the answer. Yeah.
Okay, yeah.
Can I ask a question?
Dima was asking first, but.
Can I ask a question? Anybody? No one hears me?
Yep. Sorry, yes.
Okay. Hi. have you looked at the Y system for the homogeneous time Gordon model? What happens with the Y system in this limit table, this double scaling limit?
Well, the short answer is, meaning I don't know, I guess. Meaning I haven't done much more than trying to understand that indeed this limit keeps information somehow of the massless states.
Mm-hmm. Now I'm just thinking that maybe some interesting analytic properties would appear in this limit, or some simplifications in the Y system. It might probably make the analysis more comprehensive.
Well, it should be, meaning it's definitely doable, because we know the exact limit, so, and we know meaning we have all the elements, so for that, so one should be able to actually look at the expressions once the limit is taken.
Okay, thank you.
I have a question. So I learned from the talk that massless mode mess everything up.
That massless
Mode mess everything up, even in the massive sector. This is what I learned from the talk. Is there any chance to create regime when actually they switched off? Like, well, you taught us that, virtual massless particle like changes spectrum of massive excitations. But can we do something like that? We actually ignore the existence, because then we can ask questions to solve.
To be honest, I think that the short answer is yes. Just because I know that there's I'm pretty sure, again, this was a long time ago, but there was at least one classical string solution where the world sheet and the beta ansatz solutions actually matched. So would not from the, I don't know if from the homogeneous and Gordon models, but there might be some regimes that you have in the world sheet where actually the massless excitations don't produce any. You
believe it goes on quantum level as well, beyond like?
Meaning for these solutions, the first semi-classical correction already doesn't match, right? So
okay, I see.
Because
Eva, sorry, can I just try to understand what you mean by messes things up? I mean, well, you have some generic state whose energy depends on things running in the loop from all other generic states. I don't know why that is messing anything up.
No, I mean, messing our poor understanding even more.
No, I mean, it's just some integrable mess, right? With lots of integrable things interacting with each other in lots of ways, right? You wouldn't have normally an expectation just from QFT that from 1 + 1 dimensional QFT that there would be a limit where, in fact, the massive excitations would not be affected by the math. I mean, those are the ones that are gapped, right? So, if you had, for sure, there is a limit where just the massless ones talk to each other and nothing else, right? Because those are the gapless excitations. So you could imagine scaling the mass away. But the other way around, I mean, it's just like.
No, I mean, I'm just asking, can I hope to consider a situation when my not knowledge of massless mode will not put me down?
But I don't see why you say there is not a knowledge of the massless mode. She writes down some complicated
knowledge.
not
community.
Oh, sorry.
Yeah.
I would say generically, okay. No. I think it would be specific cases where you'd find yourself, not having to worry. But again, I guess that I changed my answer to you. I don't know if there's a regime. I know there's particular cases where something magic happens that beta ansatz is enough. But I would expect that for most cases, you can't just ignore the massless states.
Okay. Yeah.
But sorry, just to clarify a little bit more there, I mean, there is still suppression. It's just not exponential, right? It's polynomial suppression. So
1 over L.
yeah. So of course, it's not great compared to if you want to do some numerics, but at sufficiently large length, you still learn stuff, right?
Yep. So they all contribute at 1 over L. Well, here at least.
So Dima, I guess the answer to your question is just make it really long. And then your intuition is good.
Yeah, I mean, well, you can guess which regime I'm interested in, so. Okay. No.
Okay. Is there any other question?
Actually, so did I understand correctly that you only have right massless S matrix?
Yeah.
So you
For this case.
You don't know any example where you would have everything right, left, right.
Not from the simplest. My experience of this SU3K would not be enough, for example, because I think you need more than one shift parameter. With just one, you couldn't do anything. It's adding more particles doesn't make a difference.
So technically, where does it appear, this shift parameter? I suppose in the S matrix. Right?
Yep. So yeah, so I can show you. That might take a, sorry. Let me see. So show, I think it's the previous one here. So basically here in the mixed mass, this is the mixed mass interactions, and you have theta plus sigma ij. Sigma ij is just either sigma or minus sigma. And these ones are just these sinh.
So it's
h divided by sigma.
basically a coupling constant of the model, is it?
Yeah.
Mm-hmm. I see. So I suppose it's probably a limit where the coupling constant goes to infinity.
Yep.
So that you would have a non-trivial still interaction left in the massless limit, right?
Yes, I think so.
Mm-hmm.
But again, I don't think that that translates to ADS-CFT, right? Because we have massive massless interactions generally. I mean, the S matrix always keeps them. So,
Right.
Well, it's a bit subtle. I mean, you can imagine taking some pure NS limit and maybe doing something else to the flux, to the NS flux as well, to try to mimic a little bit like what you're saying. But you're right, it's certainly not the generic situation. You know, so you could imagine just going to the pure NS point, and then you will only have left or left right, or right S matrices. You would not have a left S matrix. And then maybe you could play a bit more with something to do with the level K to just have left but not have right.
perhaps. Okay.
But yeah, it's not generic.
Okay, if there is no more questions, we can thank Ines again.
Thank you. I'm very sorry that this is not in person and in front of a blackboard.
Yeah, we are all sorry for that.
Would have been nice.
I've had